Okay, now let's start off with the distance formula. Now, I think most of you know this already, but just in case, say you have a point P and the coordinates are the arbitrary positions are x1 and y1, right? And for Q, it's x2 and y2. So these are the 2 points P and Q. So how do you calculate the distance between them? Well, you just square root basically the difference between the x coordinates whole square and add to that the difference of the y coordinates whole square, and the result will basically give you the distance, right? And that's very basic geometry. And you can also obviously invert the x2 and x1 and y2 and y1, because in the end it does not matter. Since both of these terms will be squared, that means they'll give you the same answer, basically a positive one. So let's see the fundamental law of trigonometry. Now we're diving a bit deeper into trigonometry. We'll be dealing with a lot of different identities, and they all stem from the fundamental law of trigonometry. And this is it. Say you have angles A and alpha and beta, okay? And they're both real numbers. So the cosine of the difference of alpha and beta is equal to cos A, cos B plus sine A, sine B. I'll be using A and B instead of alpha and beta because it's just a bit easier for me. So cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. And this is the fundamental law of trigonometry. You can, and further on we'll see other identities just like this one, but they all stem from this fundamental identity. Now, let's see the deductions from the fundamental law. We discussed the fundamental law earlier, but just to make it clear, this was the fundamental law, right? Cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. Fairly simple. Now this is the first deduction, that cosine pi by 2 plus alpha is equal to negative sine alpha. Why do we get this? Well, input this in the fundamental law. So this would become basically cosine alpha minus negative pi by 2, right? Because it's alpha plus pi by 2, and over here it's also alpha plus pi by 2 once you multiply these two negative signs, right? So in this particular case, if you compare it with the fundamental law, beta over here is negative pi by 2, right? So this becomes cosine alpha into cosine negative pi by 2 plus sine alpha into sine negative pi by 2, right? Let's see this term first. Now always remember the absolute first rule when doing these questions: draw the graph. It is very important. So let's first draw the graph of the cosine function. If you remember, the graph of the cosine function is something like this, right? Since we're dealing with the negative axis as well, the graph of the cosine function looks like this. Don't mind my drawing, but still, it is at this point, it is equal at this point pi by 2, and this is also the point negative pi by 2, and this is the point at 0 in which the value of the cosine function is basically 1. So you can see that at negative pi by 2 the value is 0. The value of the cosine function is 0. So this just becomes cosine alpha into 0. So you can cut this entire thing out because it becomes 0. Now you're left with this, the sine alpha into sine pi by 2. What is sine pi by 2? For that, you need to draw the graph of the sine function, right? So this is sine theta on the y-axis and theta on the x-axis. And so now draw the graph. The graph looks something like this, right? Let me just cut that off. It's not really a good drawing. My bad. But the sine function looks something like this on the positive theta axis, and this is how it looks on the negative theta axis. Now you can see over here, this is the point negative pi by 2, and this is the point positive pi by 2. And at negative pi by 2, the value of the sine function is negative 1, as opposed to positive pi by 2, where the value is positive 1, right? So you can see we're dealing with negative pi by 2, sine negative pi by 2, and that is equal to negative 1. So hence, this entire thing becomes equal to negative 1 into sine alpha, which is basically equal to negative sine alpha. And that's how you got this. And similarly, when you apply the fundamental law over here, you get sine beta. When you apply it on sine pi by 2 plus alpha, you get cos alpha. And basically, you need to convert the cos function into the sine function to be able to get this. And we have that over here. Once you do the conversions from the fundamental law into sine, you get this. So basically, sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. Sine alpha minus beta is equal to sine alpha cos beta minus cos alpha sine beta. Okay, you can memorize these if you want to make things quicker, but just know the actual logic behind this. And you can apply the fundamental law as well, because tan alpha plus beta is equal to, obviously it's equal to sine alpha plus beta over cos alpha plus beta, right? And the simple thing is that once you actually perform all the conversions and apply the identities on both of these, you eventually end up with this. Now, in this particular case, the derivation is slightly lengthy, right? So it's just, if you want to do it on your own, you can, but just it's easier to actually memorize this entire thing, because this is just a little bit more lengthy. And again, if you have the negative sign between alpha and beta, the only difference is that these signs are inverted, right? And that's really about it. Now, let's find the value of sine negative 780 without using the table or the calculator. Now, this is a big number. So the first thing that you must remember is that the sine function is an odd function, right? So an odd function means that basically sine negative alpha can be written down as negative sine alpha, which means that sine negative 780 can be written down as negative sine 780. Okay, the first rule. Now, since we're dealing with the sine functions, what was the first rule? The first rule was that draw the graph. Okay, so draw the graph of the sine function. Okay, now here's the thing. You know that the sine function completes one wave in 2 pi or 360 degrees, which means that the second revolution, the second complete cycle, will complete at 720 degrees, right? This is 720 degrees. And so 780 means that 720 plus 60. So basically it's more or less like around this particular point, right? Let's just complete this cycle as well, which means that 780 is at this particular point, more or less. So this is 780 degrees. Okay, so theta at 780 degrees, we do not know what the y value, it must be somewhere around here, less than 1, because that's the maximum, but it's somewhere around here, right? We do not know what it is. Okay, now here's the thing. To solve this particular example, what do you do? Well, you can find a very weird thing over here. At basically 2 pi by 2, the value of the function is 0. And at 4 pi by 2, or let's not use pi by 2 here, let's use since we're dealing with degrees over here, let's not deal it with pi by 2. Let's just use the degrees. At 90 degrees, this is 90 degrees, by the way, it's equal to 1, right? So at 2 times 90 is equal to 0. Again, at 4 times 90 degrees, it's also equal to 0. At 6 times 90 degrees, it's again 0. At 8 times 90 degrees, it's again 0. So you can see the relation here. At every single even multiple of 90 degrees, the value of the function is 0, right? So you can use that same logic over here. You need to first, the thing that you need to do is you need to divide the number, which is 780 over here, by 90. Okay, and once you do that, you get the multiple, and that over here is 8, and the remainder is 60 degrees. So the even multiple over here is 8, which means that 720 degrees, which is this point here in the graph, that is your starting point. And you go ahead from that 720 degree point by 60 degrees, right? So here's what you do. You replace the 780 with 8 times 90 plus 60. Now 8 times 90 is an even multiple of 90 degrees, which means that this entire thing becomes 0. And you move on from that point by 60 degrees, right? So sine 780 is basically just equal to sine 60. So negative sine 80 is equal to negative sine 60. And as we all know, that is equal to negative under root 3 by 2, because sine 60 is equal to under root 3 by 2. And there is a whole logic behind why that is, but that is just way too basic at this level. You should know this by now. But you can use the calculator to calculate this as well. And I hope this makes sense. Just remember, even multiples of 90 degrees or even multiples of pi by 2 always give the value 0 for a sine function. And you'll use that always as a reference point when calculating larger numbers like 780 degrees. Now let's see that how we can express sine 196 degrees as a trigonometric function of an angle that is less than 45 degrees. Now, here's what you do. As you know that a sine function, the first rule is to draw the graph. You know that the sine function looks something like this. Here's one full cycle, and then this cycle just repeats itself on and on until infinity, right? And this is the theta axis, and this is the sine theta axis. So when theta is 180 or multiples of 180, so basically 360 and whatever 360 plus 180 is, what's that? 540, I believe, or 404. I think it's yeah, it's 540 degrees, and then at 720 degrees and multiples of pi, the value of the function reaches 0, right? So first you need to identify what value is, what multiple of 180 is closest to 196, and that's obviously 180, right? So sine 180 plus what gives you 196? 16. 180 plus 16 gives you 196. Now that you've written it in this form, you can apply the double angle formula. And the reason we took 180 is because we can now, once you apply the trigonometric formula, you know that sine A plus B is equal to sine A cos B plus cos A sine B. So A is obviously 180 and B is 16. So this becomes sine 180 cos 16 plus cos 180 sine 16. And now you can see why we use the multiples of 180 degrees, because sine 180 can be written down as 0. So 0 into cos 16 is 0. So you can cancel this out. And cos 180, well, you draw the graph of the cos function as well. Now you know the cos function starts here and then it goes like this. This is 1 cycle, this is 2 cycle, and so forth, right? And you know that at 180 degrees, which is this here, the value of the function is -1. So -1 into sine 16. And eventually that gives you negative sine 16. So you've expressed sine 196 as a trigonometric function of an angle that is less than 45, because 16 is less than 45. Now another way to just verify this is because, as you know, if you look at this sine function again, 180 plus 16 is roughly, this 196 is just roughly somewhere around here. And on the y-axis, this value is negative something, less than negative 1, obviously, because that's the maximum point over here. And that is at, I think, 270 degrees. But yeah, it's somewhere around here. Let's call this negative x, okay? And basically, sine 16 is over here, right? And that is exactly the same length as negative x from the 0th position, except it's in the positive y-axis, right? So this is x. And so when you just write down negative sine 16 or negative sine x, that gives you the same value as sine 196, right? And that's just a very simple way of verifying this. But again, you don't need to do that. You just need this for this trigonometric identity, and you can just solve this thing directly. Okay. Now, we need to prove that the left-hand side over here is equal to the right-hand side, which is just -1. So we need to simplify this entire left-hand side in a way that gives us -1 in the end. So we're using the formula to prove that the trigonometric identities are equal. Let's look at the left-hand side. We need to just look at each individual case over here, each individual trigonometric function. Okay, so let's look at cos 90 plus theta first. As you know, we've used this identity before, that cos pi by 2 plus alpha is equal to sine alpha, and pi by 2 is just 90 degrees in radian, so this is just basically equal to cos 90 plus alpha. So cos 90 plus alpha is equal to negative sine alpha, so that means cos 90 plus theta is equal to negative sine theta. Okay, that's established. Secant negative theta is equal to secant theta. Why? Because secant theta is equal to 1 over cos theta, and you know that cos is it's an even function, so 1 over cos negative theta would give you 1 over cos theta, and that is equal to secant theta. Okay, so that's why we have this over here. And tan 180 minus theta is equal to negative tan theta. And again, if you use this trigonometric identity over here, and you replace this alpha with 180, and you replace this beta with theta, and input the values over here, you eventually end up with negative tan theta. And now let's look at this. Secant 360 minus theta is equal to secant theta. Why? Because over here, again, remember, secant is the reciprocal of the cos function. So first look at this. Cos alpha minus beta is equal to cos alpha cos beta plus sine alpha sine beta. And if you replace this alpha with 360 and this beta with theta, you eventually end up with this over here, except now you have to take its reciprocal. That's just fairly simple. So this entire thing just basically becomes, let me just write that down, 1 over cos 360 minus theta is basically just equal to 1 over cos alpha cos beta, and alpha is 360, so cos 360 cos theta plus sine 360 sine theta. Okay, so again, cos 360 is equal to positive 1, right? So this becomes 1 over 1 plus sorry, no, not 1 multiplied by cos theta, so that becomes cos theta plus sine 360 is equal to 0, so you can cancel this entire term out. So eventually you're just left with 1 over cos theta, which is secant theta, and that's what you have here. Okay, now sine 180 plus theta, again, you use this identity, you end up with negative sine theta. Cotangent 90 minus theta, you apply this identity, but again, like in the case of the secant, cotangent is the reciprocal of the tangent function. So again, you take the reciprocal of whatever you obtain over here. Okay, so now once you obtained all of these values, you start replacing them. We established that cos 90 plus theta is equal to negative sine theta, secant theta is equal to secant negative theta is equal to secant theta, tan 180 minus theta is equal to negative tan theta, secant 360 minus theta is equal to secant theta, sine 180 plus theta is equal to negative sine theta, and cotangent 90 minus theta is equal to tangent theta. Now you start cancelling them out. You can cancel this out and this out. You can cancel the secant theta and this secant theta out, and you can cancel this negative tan theta with tan theta, except you're left with negative 1, which is why you end up with negative 1 in the end. And that's how you prove that the left-hand side is equal to the right-hand side. Now, we need to prove that the equation, and then we need to prove the equation by using angles of a triangle. So, it says that if alpha, beta, and gamma are the angles of a triangle ABC, then prove that sine alpha plus beta is equal to sine gamma. Okay, how do we do this? Well, it says that sine alpha plus beta is equal to sine gamma. How? Let's see. As you know that the three angles in a triangle always equal 180 degrees, right? So alpha plus beta plus gamma is equal to 180 degrees. Now, since we have this alpha plus beta on the left hand side and this gamma on the right hand side, let's take this gamma to the right hand side. And that gives you alpha plus beta is equal to 180 minus gamma. Now apply the sine function on the left hand side and the right hand side. That means sine alpha plus beta is equal to sine 180 minus gamma. And as you know, sine 180 minus anything gives you minus sine that anything. Sorry, not minus sine, just sine that anything. Because again, if you draw the function of the sine, that looks something like this, right? And so basically, if this is 180 degrees, and let's say 180 minus gamma is less than 180, obviously. So let's say that's somewhere around here, okay? And this, since this is 180 minus, oh, sorry, let's just write that, yeah. So this is at 180 minus gamma, okay? And if you just look at this over here, it's basically just equal to 0 plus gamma, right? Because over here, this point is 0 plus gamma. And that gives you the same value, which is why sine 180 minus gamma is equal to sine 0 plus gamma, which means that this entire thing becomes equal to sine gamma. And that's really just simple. Always remember that these, till this point here, this middle point of the sine function, both of these sides, this side and this side, are symmetrical. So if you move gamma, an angle gamma from the right hand side, it's the same as moving the angle gamma from this side, the left hand side. Okay? Now, let's find the value of the sine and cos function at the angle of 15 degrees. So we need to find sine 15 first. Now, remember that if you, God forbid, you do not have a calculator, or you just end up with a really, really bad professor, and he tells you to find sine 15. What do? Well, we have some things that were taught beforehand. We know that cos 60 is equal to under root 3 by 2. Okay, we know that sine 60 is equal to 1 by 2. Sorry, I'm just mixing that. Sine 60 is equal to under root 3 by 2, and cos 60 is equal to 1 by 2. Okay, we know these two, and we know that sine 45 is equal to 1 by under root 2, and we know that cos 45 is also equal to 1 by under root 2. Okay, you can draw the triangles for them and verify them, but we just know these because, well, in my country, that's just the standard practice to know these values. You can just draw the triangle and figure them out. But you can write down sine 15 as sine 60 minus 45, right? And once you apply the trigonometric identity on this, you find out that sine 60 minus 45 is equal to sine 60 cos 45 minus cos 60 sine 45. Well, now you can replace the values that you already know. You know that sine 60 is under root 3 by 2. You know that cos 45 is 1 by under root 2. You know that cos 60 is 1 by 2. And you know that sine 45 is 1 by under root 2. And that eventually gives you this value. So now you've just beaten the professor. And again, for cos 15, remember the same values. You can apply them over here. You can write down cos 15 as cos 60 minus 45. Okay, now you apply the identity for the cos function. Cos 60 minus 45 can be written down as cos 60 cos 45 plus sine 60 sine 45. And again, you replace those values. Cos 60 is 1 by 2. Oops, sorry. Cos 60 is 1 by 2. Cos 45 is 1 over under root 2. And sine 60 is under root 3 by 2. And sine 45 is 1 by under root 2. And once you do all the multiplication, you end up with this. And so, without using the calculator and by using the trigonometric identities, you found out that the value of the sine and cos functions of the angle 15 degrees is just very simple. Okay, let's prove the left and right hand side of the trigonometric function. Okay, we have to prove that this left hand side is equal to this right hand side by applying different trigonometric identities and properties. Now it's easier to just expand the trigonometric function instead of contract it. So let's take the left hand side. Let's prove that this sine 45 plus alpha is equal to this 1 by under root 2 into sine alpha plus cos alpha. Okay, because you can see that this looks very familiar. This left hand side looks very familiar. Yeah, we can apply the trigonometric identity on it. We can write down sine 45 plus alpha as sine 45 cos alpha plus cos 45 sine alpha. Okay, at this point you should know this. And as you know that sine 45 is equal to 1 by under root 2 and cos 45 is also equal to 1 by under root 2. Okay, now we write that down and you have this. And very simply, you can take this 1 by under root 2 common from this term and this term, and now you've proven that the left hand side is equal to the right hand side, right? It's very easy. Now, let's look at the sum of tangent functions. Again, we have to prove that the left hand side is equal to the right hand side. Okay, now obviously in this particular case you'll take the left hand side and you'll prove that it is equal to 0, because again, expanding 0, there are just a million ways to expand 0. It can be equal to 1 minus 1, 2 minus 2, I don't know, 3 divided by 0 divided by 3, and so forth. So yeah, you take the left hand side in this case, and let's prove that it is equal to 0. Now you have this again. Now look, it looks familiar, right? This and this, it looks familiar. You can apply the trigonometric identity of the tangent function on it. Now tan pi by 4 minus theta, it can be written down as tan pi by 4 minus tan theta plus over 1 plus tan pi by 4 tan theta. And again, you apply the same identity on this tan 3 pi by 4 plus theta, that is equal to tan 3 pi by 4 plus, right? Because over here it's minus because this is minus, and over here it's plus because this is plus, right? And at the denominator the signs are just inversed as well. Okay, now this is equal to tan 3 pi by 4 plus tan theta over 1 minus tan 3 pi by 4 tan theta. Fairly simple. Now let's see how it becomes 0. Now, as you know, tan pi by 4 is equal to 1, right? And tan theta is as it is. And again, this tan pi by 4 is equal to 1. So this entire term just becomes tan theta. So you have this tan theta. Okay. Tan 3 pi by 4 is equal to negative 1, right? And tan theta is just tan theta. And again, you apply this negative 1 over here, and this negative sign multiplied by this negative 1 becomes a positive sign, and you're just left with this tan theta over here. Now, you can just take the LCM of this and this, it's just equal. So now you can just add the numerators up because the denominators are equal. So it becomes 1 minus tan theta minus 1 plus tan theta. You can subtract this, these ones, you can subtract these tan thetas, and so you get 0 over 1 plus tan theta, which is simply equal to 0, and hence you've proven the right hand side. Okay, so let's prove that cotangent A plus B is equal to cotangent A cotangent B minus 1 over cotangent A plus cotangent B. Now, a very simple way of just looking at this is, you know that these are equal, right? Because cotangent is basically the reciprocal of the reciprocal of the tangent function, right? So sorry, of the tangent function. And so you can see that this looks familiar, this right hand side, right? It's the reciprocal of the tangent A plus B identity, right? Okay, but let's just prove how this happened. Okay, first let's take the left hand side. Okay, so you already know that cotangent is the reciprocal of the tangent function. So instead of sine over cos, it's cos over sine. So cotangent A plus B is equal to cos A plus B over sine A plus B, right? As opposed to sine A plus B over cos A plus B, which would be the case for tangent A plus B. I'm sorry, there's just some construction going outside, but yeah, I don't mind that. Okay, so now that you have this, you can apply the trigonometric identities for the cos a plus b function and the sine a plus b function in the numerator and denominator respectively. And so you end up with this. Okay, so cos a plus b is equal to cos a cos b minus sine a sine b, and sine a plus b is equal to sine a cos b plus cos a sine b. Fairly simple. But now look at this. Look at this over here, the right hand side, and look at this here, right? These two should be equal, obviously, right? So this is equal to cotangent a cotangent b minus 1 over cotangent a plus cotangent b. Now look at these two. You can see this negative sign and this negative sign. They correspond to each other. This positive sign and this positive sign, they correspond to each other. So basically, cos a cos b must become equal to cotangent a cotangent b. Sine a sine b must equal 1. Sine a cos b must equal cotangent a. Cos a sine b must equal cotangent b. Okay, so the easiest thing you can see here is that if you divide this sine a sine b by sine a sine b, you end up with 1. So now just divide the entire function. Divide this entire function by sine divided by so basically, instead of dividing it, multiply this entire function by 1 over sine a sine b over the same thing, right? Because again, the total value of the function must not change when you multiply it with something. So yeah, this entire thing becomes 1. So yeah, the value of the function does not change. But now, once you do this, it becomes this. Once you multiply this with this entire thing, right, you end up with this. So cos a cos b divided by sine a sine b, sine a sine b divided by sine a sine b, sine a cos b divided by sine a sine b, and cos a sine b divided by sine a sine b. Okay, so now that you've successfully multiplied it, you can see that this and this cancel out, so you're just left with 1. And let's just see what happens. We had this, so now this and this cancel out, you're left with 1. Cos a cos b over sine a sine b, that just becomes cos a over sine a becomes cotangent a, cos b over sine b becomes cotangent b. Fair enough. Okay, sine a cos b over sine a sine b. This sine a and this sine a cancel out, so you're just left with cos b over sine b, which is cotangent b. Okay, cos a sine b over sine a sine b. The sine b's cancel out, and you're just left with cos a over sine a, so you just end up with cotangent a. And now you've proven that the left hand side is equal to the right hand side. Okay, so this is an interesting question. It says that we have to find sine alpha plus beta, and the information that is given to us is this. Sine alpha is equal to 4 by 5. Sine beta is equal to 12 by 13. And it says that this alpha lies between pi by 2 and pi. And this beta also lies between pi by 2 and pi. So what that means is if you draw the quadrants, right, for the circular coordinates, you know that this positive y-axis is at pi by 2. The positive x-axis is obviously 0, right? So if you move in a circle, this is pi by 2. The negative x-axis is pi, the negative y-axis is 3 pi by 2, and the positive x-axis is again 0 or 2 pi, right? It's the same thing, because once you complete one revolution, it's 2 pi, which means that you're basically back to the 0th point. Okay, so sine alpha plus beta, how do we find it? We only have sine alpha and sine beta. Now you can apply the trigonometric identity over here. You know that sine alpha plus beta is equal to sine alpha cos beta plus sine beta cos alpha, right? So basically what you need now is cos beta and cos alpha. How do you find that? Well, sine alpha is given to us, and we have already established that it lies between pi and pi by 2. Now, if you look at the quadrant graph over here, alpha lies between pi by 2 and pi, which means it lies in the second quadrant. And as we all know, only the sine function is positive in the second quadrant. Only the cos function is positive in the third quadrant. Only the tan function is positive in the fourth quadrant. And all of the functions are positive in the first quadrant. But this lies in the second quadrant, so only the sine function is positive. Okay, fair enough. Now, you know the formula that sine square alpha plus cos square alpha is equal to 1. We need to make use of these sine alpha and sine beta to actually find cos alpha and cos beta. So you can take this sine alpha to the right hand side, so it becomes 1 minus sine alpha, sine square alpha, and once you take the under root of that, you can find cos alpha. Fair enough. So cos alpha is equal to under root 1 minus sine square alpha. Okay, we already have sine alpha, which is 4 by 5. So 1 minus 4 by 5 whole square is basically equal to 1 minus 16 by 25, because 4 square is 16 and 5 square is 25. Okay, now you can take the LCM, multiply this 1 with 25 and also divide it by 25. So you get 25 over 25. So you can now basically add up the numerators, 25 and 16. So 25 minus 16, because of this negative sign here, and that over 25. 25 minus 16 over 25. That becomes 9 over 25. Take the under root of 9 over 25, what do you get? You get positive or negative 3 by 5. Now, we have already established that cos alpha is equal to positive or negative 25. But we only take negative 3 by 5. Why? Because alpha lies in the second quadrant, and as we all know, in the second quadrant, only sine function is positive, right? So this is the cos function, so it must be negative. Hence, we take negative 3 by 5, not positive 3 by 5. Okay, now we know that sine b is equal to 12 by 13. We'll apply the same logic to find cos beta. Cos beta is equal to 1 minus sine square beta whole under root. Fair enough. Now, obviously, sine square beta is equal to 12 square over 13 square, which is 144 over 169. And again, you can multiply this 1 over here with 169 and also divide it by 169 to take the LCM. Once you take the LCM, you find out that the numerator becomes 169 minus 144, and the denominator is obviously 169. Now, 169 minus 144 over 169 is equal to 25 divided by 169. And again, you take the under root of all of that, and you end up with positive and negative 5 by 13. Fair enough. But again, this is a cos function, and the angle beta also lies in the second quadrant, which means that again, you'll have to take negative 5 by 13 instead of positive 5 by 13. Because again, the second quadrant means that only the sine function is positive, and this is a cos function, so it will be negative. Now, we know that sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. So you can now basically just multiply the values that you found. We found out that we already given that sine alpha is 4 by 5. We found out that cos beta is negative 5 by 13. We know that cos alpha, we already know that sine beta is equal to 12 by 13, and we found out that cos alpha is equal to negative 3 by 5. Once you do all the multiplications and the calculations, you end up with 56 over 65. And that is the value of sine alpha plus beta. Now, let's prove that the equation that the sum of cotangent functions is equal to 1. We need to prove the equation. So the question states that alpha plus beta plus gamma is equal to 180 degrees, right? And so basically these are the three angles of a triangle. And it says that cotangent alpha, cotangent beta plus cotangent beta, cotangent gamma plus cotangent gamma, cotangent alpha is equal to 1. And we need to prove it. Okay. So the first thing that is given to us is that alpha plus beta plus gamma is equal to 180 degrees. Fair enough. Now, once you take the gamma to the right hand side, it becomes negative gamma. So you have this. So alpha plus beta is equal to 180 minus gamma. Now apply the tangent function on the left hand side and the right hand side. So you end up with this. Fairly simple. And now use the trigonometric identity, which states that tan alpha plus beta is equal to tan alpha plus tan beta over 1 minus tan alpha tan beta. And you apply the same property over here and you end up with negative tan gamma. Why? Because tan, this can be written down as tan 180 plus tangent, sorry, not plus, negative, because this is negative, right? So minus tangent gamma. I'm sorry for my drawing, it's just a little bit off. Okay, over 1 plus, not minus, because again it's not a positive sign, it's a negative sign between 180 and a gamma. So 1 plus tangent of 180, oops, sorry, tangent of 180 into tangent of gamma. Okay, now tangent 180 is equal to 0. Okay, we already know that that's equal to 0. So eventually you just end up with negative, this becomes 0, you cancel it out, and again, since this is 0, this entire term tan 180 into tan gamma is also equal to 0. So you just end up with negative tan gamma, which is why you have it over here. Okay, now that we've established that, you now take the reciprocal of all the tans over here and you get the cot functions. Why? Because we're dealing with the cotangent function in the question itself. So you convert every tan function into cotangent by taking the reciprocal. So tan alpha becomes 1 over cotangent alpha, tan beta becomes 1 over cotangent beta, and that's the same over here as well and here as well. And similarly, this tan gamma becomes 1 over cotangent gamma. Fair enough. So you have this. And now, once you take the LCM in the denominator and the numerator, you get this, right? And now that you have this, again, this happens because if you take the LCM over here in the numerator, you basically multiply this with cotangent beta and the denominator with cotangent beta as well. And so you have in over here, let me just write this down. So this becomes basically cotangent beta plus cotangent alpha over cotangent alpha cotangent beta. And this entire thing is now divided by 1 minus whatever this is, and when you take the LCM of this over here, what do you get? Well, 1 will be multiplied with cotangent alpha cotangent beta, so it becomes cotangent alpha cotangent beta minus 1 over cotangent alpha cotangent beta, right? And now this and this can be cancelled out and you're eventually left with this. Fair enough. So now that you have this, what you do is you cross multiply, right? Cross multiply this and cross multiply this. So you get this cotangent gamma into cotangent alpha plus cotangent beta is equal to negative cotangent alpha cotangent beta minus 1. Okay. Now you multiply and expand. So this becomes cotangent alpha cotangent gamma plus cotangent beta cotangent gamma is equal to negative cotangent alpha cotangent beta plus, because this negative and this negative multiply, so plus 1. Okay. And now when you take this term cotangent alpha, cotangent beta, this negative cotangent alpha, cotangent beta, to the left-hand side, you eventually prove the question itself. And that's what we had to do. Now, this question states that we need to express this expression in this form. So what we need to do is we need to find the value of r, and we need to find the value of this phi. Okay, to find the value of r, it's fairly simple. It's the magnitude or the radius of this entire expression. And you just find that out by finding the square of whatever is being multiplied with the sine term and the square of whatever is being multiplied with the cos term, in this case 12 and 15 respectively. Add the squares up and take the under root. In this particular case, it ends up being 13. We found the value of r. But now we need to find the value of this phi. Okay, how do we do that? Standard procedure is that basically you can write this down like this, right? We found out the value of r as 13, and now basically you need to, since 13 is being multiplied with sine theta, with 12 sine theta, you also have to divide 12 sine theta by 13, and same goes for 5 cos theta. Since 13 is being multiplied with 5 cos theta, you need to divide it by 13 as well, so that the actual value of the function does not change. Okay, fairly simple so far. Now look at this. You need to express this in this form, right? R sine theta plus phi. So do substitutions. How? Well, basically you can replace this 12 by 13 with cos phi. You can replace this phi by 13 with sine phi. You're assuming that cos phi is equal to 12 by 13 and sine phi is equal to phi by 13. Now why do we do that? Well, because the first thing we need to do is express this entire thing like this. And why do we need to do that? Now, do you remember the sine identity? Looks familiar, right? Because sine alpha plus beta is equal to sine alpha cos beta plus sine beta cos alpha. And if you treat alpha as theta and beta as phi, well, you can now write this entire thing as sine theta plus phi. So now you have it in this form, except you do not know the value of phi yet, right? So how do we do that? Well, you know that cos phi is equal to 12 by 13. You know that sine phi is equal to 5 by 13. What's tan phi? It's just sine phi divided by cos phi. And that just ends up being, well, let's just do it by hand. Sine phi over cos phi. That means 12 by not 12 by 13, sorry, 5 by 13 divided by 12 by 13, and that ends up being 5 by 12, not 13, it's 12. So now phi is equal to tan inverse of 5 by 12, and once you find out this value of phi, just replace it into this phi over here, right? And then you have the true value of the function in the form r sine of theta plus phi. Now let's see what the double angle identities, the half angle identities, and triple angle identities are. So again, everything can be proven by the fundamental law of trigonometry. Okay, we already discussed this before many times, and we do not need to exactly know how we got all of these identities. You can just prove them by using the identities before, and I'll give you an example as well. But we do not need to prove everything. Just know that these will be given to you, or you'll have to memorize them just to make your life a bit easier. But again, all of these can be proven as well. And here's an example. Sine 2 alpha. Well, how did it become 2 sine alpha cos alpha? Now, you know that sine alpha plus beta is equal to sine alpha cos beta plus sine beta cos alpha. Okay, now if you replace this beta with another alpha, it becomes sine alpha plus alpha, and that becomes sine alpha cos alpha plus sine alpha cos alpha, which is equal to 2 sine alpha cos alpha, and hence you have the proof for this sine 2 alpha. Okay, and you can do the same for this cos 2 alpha as well, right? You can apply the formula for cos alpha plus beta over here, right? Alpha plus beta, cos alpha plus beta is equal to cos alpha cos beta minus sine alpha sine beta. Now, if you replace this beta with another alpha, you get cos 2 alpha, and hence eventually this becomes cos alpha into cos alpha, which is cos square alpha, and this becomes sine alpha sine alpha, which is also equal to sine square alpha. And again, if you use the property that sine square alpha plus cos square alpha is equal to 1, you can get these as well, right? Because you can replace this sine square alpha with 1 minus cos square alpha, and you can also get this as well, right? If you just replace this cos square alpha with 1 minus sine square alpha, right? And you have proofs for everything. You have proofs for this as well. If you just use the tan alpha plus beta property, you get this, okay? Just as you did with cos and sine. So now you do not need to worry yourselves with how we got these. Everything is proven to you beforehand. And you can use the same properties to get these identities as well, right? So the basic thing is that cos alpha plus cos alpha over 2 is equal to 1 plus cos alpha over 2 whole under root. The only difference between cos alpha over 2 and sine alpha over 2 is this sign over here, right? These are just shortcuts for you to memorize. Okay, so cos alpha over 2 and sine alpha over 2 only have this difference, and tan alpha over 2 is basically just sine alpha over 2 over cos alpha over 2, and that ends up just becoming equal to this. Okay, and yeah, so that's the half angle properties, and these are the triple angle properties that are very rarely ever used, but still you need to know them. So cos 3 alpha, again, you can prove this by the fundamental law and all the identities that we discussed beforehand. It ends up being equal to this. Just memorize them or they'll be given to you. Sine 3 alpha is equal to this. So you can see that the difference between cos 3 alpha and sine alpha is again very minimal, right? Basically, instead of the signs are opposite and the functions are also opposite. So cos cube alpha, 4 cos cube alpha can be written down as minus 4 sine cube alpha, and minus 3 cos alpha will be written down as 3 sine alpha, right? So that's the relation between cos 3 alpha and sine 3 alpha. And tan 3 alpha is, again, if you divide sine 3 alpha by cos 3 alpha, you end up with this. Fairly simple, right? Or you can use the initial identities with the fundamental law. Okay, but here's the thing. Now let's do a question regarding this. Okay, it says that we have to find the value of sine 2 alpha, cos 2 alpha, and tan 2 alpha. Now these are the double angle identities. It says that sine alpha is equal to 12 by 13. Okay, we'll apply the double angle identity to find sine 2 alpha. Now, sine 2 alpha is equal to 2 sine alpha cos alpha. Okay, so sine alpha is equal to 12 over 13. We need to find cos alpha as well. Okay, and since the values are positive, so alpha lies between 0 and pi by 2. Okay, So sine alpha is equal to 12 by 13. So cos alpha is equal to under root 1 minus sine square alpha. And since sine alpha is 12 by 13, sine square alpha is 144 by 169. Basically 12 square over 13 square. And using that, you get the value as 5 by 13. And since alpha is in the first quadrant, this will be positive, as all functions are positive in the first quadrant. Okay. And we already know that sine 2 alpha is equal to 2 sine alpha cos alpha. So you already have sine alpha, we found cos alpha. So eventually sine 2 alpha becomes equal to 120 over 169. Fairly simple. Now cos 2 alpha, that's equal to cos square alpha minus sine square alpha. And we already found out what cos alpha is, and we already know what sine alpha is. So just take the squares of both and subtract them. Simple. You get minus 119 over 169. Simple. Now, tan 2 alpha is just sine 2 alpha over cos 2 alpha. You do not need to use the identity, the double angle identity of tan 2 alpha. Just make your life simple. Divide sine 2 alpha and cos 2 alpha. We already found them out, and so just divide them. So 120 over 169 divided by negative 119 over 169. And that is equal to minus 120 over 119. So yeah, this is tan 2 alpha. Fairly simple, right? Now let's prove the trigonometric equation by using double angle formulas. So it says that cotangent alpha minus tangent alpha is equal to 2 cotangent 2 alpha. Let's take the left hand side and let's prove that it is equal to the right hand side. The left hand side states that cotangent alpha minus tangent alpha is equal to 2 cotangent 2 alpha, and now cotangent alpha is obviously equal to cosine alpha over sine alpha, and tangent alpha is equal to sine alpha over cosine alpha. Now that that's established, let's take the LCM, right? Because these are two separate terms separated by the negative sign, but on the right hand side it's just one term. So to get one term, you need to take the LCM over here, right? And so multiply this entire expression with cosine alpha and multiply this entire expression with sine alpha, and now you have this term over here. Now this looks familiar, right? That's because it's the double angle identity of the cosine function, which states that cosine 2 alpha is equal to cosine square alpha minus sine square alpha. So now this can be written down as cosine 2 alpha over sine alpha cosine alpha. But look at this. It says that we need cotangent 2 alpha. And how do you get cotangent 2 alpha? Well, you need sine of 2 alpha in this denominator over here, right? So that cosine 2a divided by sine 2a becomes cotangent 2a. So how do you do that? Well, if this denominator becomes 2 sine alpha cosine alpha, you can use the double angle identity of sine 2 alpha, which states that sine 2 alpha is equal to 2 sine alpha cosine alpha. And to get that, you need to basically multiply this denominator of sine alpha cos alpha with this 2. And since you're multiplying the denominator with 2, you need to multiply the numerator with 2 as well, so that the actual value of the function does not change. So multiply this cosine 2 alpha with 2 and multiply this denominator with 2 as well. And so you get 2 cosine 2a over 2 sine a cosine a, right? And now you can apply this identity in this denominator. And so you get 2 cosine 2a over sine 2a. And now cosine 2a over sine 2a becomes cotangent 2a. And so you're eventually left with this. And now you've proven that the left hand side and the right hand side are equal. Now let's find the solution of a half angle trigonometric equation. And we'll use the half angle property over here. So we need to prove that this left-hand side of the equation is equal to this right-hand side, and basically we'll take the left-hand side in this case because it's easier to go from a bigger expression to a smaller expression, and the bigger expression is on the left-hand side over here. Okay, and we'll apply the properties on it to eventually turn it into the right-hand side. We have this. So first let's just turn it into its easier, more familiar counterpart. So cosecant theta becomes 1 over sine theta, and cosecant 2 theta becomes 1 over sine 2 theta, and secant theta becomes 1 over cos theta. Very simple. Now let's turn it into a more recognizable form, which is this. Basically, we just have to eliminate this fraction sign. So we replace it with the division sign and then the multiplication sign, after which we take the reciprocal of 1 over cos theta, because from when we convert from division to multiplication, we take the reciprocal of the expression that is after it. Okay, and that's just fairly simple math so far. Okay, so we have this. Now what do? Well, you'll take the LCM over here to turn the entire expression inside the bracket into one expression, that is without this plus sign. Okay, so once you take the LCM, you get this. And now what do? Well, first apply the half angle identity over here. Now we all know that the half angle identity of cos A by 2, right, is equal to under root 1 plus cos A over 2, and the entire of this is in the under root. Okay, and once you need to get this particular term, right? And how do you do that? Well, first you need to take the square of both sides. Okay, so you take square over here and square over here so that you can eliminate this under root sign. Okay, so this square term is eliminated with this under root sign, and so you get cos square A by 2 is equal to 1 plus cos A. But we have only cos theta plus 1 over here, so you take this over 2, by the way, and so you take this 2 to the right hand side, and so 1 plus cos A becomes equal to 2 cos square A by 2. And if you just replace this A over here with theta, you can replace cos theta plus 1 with 2 cos square theta by 2. Okay, and this is the proof. And now what do you do with the denominator? Well, first you cancel out this cos theta and this cos theta. Okay, so you're just left with sine theta, but we need half angles over here, not full angles. So we need theta by 2. So how do you convert sine theta into theta by 2? Well, you know the double angle identity that says that sine 2a is equal to 2 sine a cos a, right? So the multiple is over here, and so you can also write basically sine a is equal to 2 sine a by 2 cos a by 2, right? Because these are the angles and the double of the angle is over here. So these are the angles a by 2, and the double of a by 2 is a. So you apply the same property on sine theta. So sine theta becomes 2 sine theta by 2 cos theta by 2, like sine alpha was equal to 2 sine alpha by 2 cos alpha by 2. And so you get this. And now you can just cancel out this this cos theta with 1 of the cos theta in the denominator, in the numerator. So you're left with, and you can also cancel out this 2, by the way. So you're just left with cos theta by 2 over sine theta by 2. And that just becomes cotangent theta by 2, and that was equal to the right hand side. And so we've proven that the left hand side is equal to the right hand side. Now let's reduce the fourth power to the first power. So the question says that we have to reduce sine theta to the power 4 to an expression involving only a function of a multiple of theta raised to the first power. So what this means is that basically you need to convert this sine theta to the power 4 into a constant
being multiplied with a function of theta, but the condition on this is that it must be a linear expression of theta. Okay, so there must not be any square terms after the constant, not a single one, not even the bracket. That must not be a square term either. Okay, so how do you do that? Well, we obviously will need to use identities, and we only know how to use identities on squares of trigonometric functions. So the first thing logically would be to convert this sine theta to the power 4 into sine square theta whole to the power 2. Okay, so now we have to deal with just this sine theta inside, sine square theta inside this bracket. So the first thing you'll do is you'll have to apply the half angle identity on it. So so that this square term inside can be eliminated. So once you apply the half angle identity on sine square theta, you get 1 minus cos 2 theta over 2. And I've told you how to do these half angle identities before, but again, let me just show you a simple way of how we got here. It's because sine theta by 2 is equal to under root of 1 minus cos theta over 2. And so now instead of this theta by 2 you have theta, so obviously instead of this theta you'll have 2 theta. Okay, and obviously since it's sine square theta, that means this entire term must be square, and this one as well, this will be square as well, so you can cancel out this square term. And so that's why you have 1 minus cos 2 theta over 2 instead of under root 1 minus cos 2 theta over 2. Okay, so this is a smaller explanation, but now we need to eliminate this square as well, the square that is applied on the bracket. So the first thing you'll have to do is take this divided by 2, which means basically being multiplied with 1 by 2 outside of this bracket. So you'll take, so this is not 1 by 2, it will be 1 by 4 outside of the bracket because of this square. So it will become 1 by 2 square outside, so 1 by 4. And then you'll take the square of the numerator, which is 1 minus cos 2 theta. So once you expand 1 minus cos 2 theta whole square, once you expand that, you get this 1 minus 2 cos 2 theta plus cos square 2 theta. Okay, fairly simple so far. But now we have another square term over here, and we need to eliminate that. So again, you'll apply the half angle identity on it, and so you'll get this 1 plus cos 4 theta over 2. And what you'll do now is you'll take the LCM over here. So you can take this, so eventually you can take this term outside with this 1 by 4. So once you take the LCM, you basically get this entire term divided by 2. And obviously once you take that 2 outside and multiply that 1 by 2 out, when you take this 1 by 2 outside and multiply it with 1 by 4, you get 1 by 8. Okay, which is why you have this 1 by 8 over here. And now you have a constant 1 by 8 multiplied with a linear function of theta, because there is no square term at all anywhere. And so you can just again add this 1 to this 2 and you get this. So yeah, that's how you do the question. Now let's see the sum and difference of sines and cosines. How do we convert them into a different form? So it says that if you have sine alpha plus beta plus sine alpha minus beta, that is basically equal to 2 sine alpha cos beta. And you can apply similar logics on all of these, right? So 2 cos alpha sine beta is equal to sine alpha plus beta minus sine alpha minus beta. 2 cos alpha cos beta is equal to cos alpha plus beta plus cos alpha minus beta. And minus 2 sine alpha sine beta is equal to cos alpha plus beta minus cos alpha minus beta, right? So basically you have just this alpha plus beta and alpha minus beta, and you just apply the sine and cos terms with either a positive sign or a negative sign between them, right? Positive, negative. and you need to convert them into one term instead of two separate terms. So this is how you do it. These are all the sum and difference formulas. And again, all of these can be traced back to the fundamental theory, and we'll not really go into the detail of that. You just know how to do that, and it's very simple to memorize, right? It's not really that difficult. It's just the same thing in just different formats. Okay. And if you just want to find out how we got here, you can apply the fundamental theorem and all the different identities on all of these right hand side expressions, right? And you can eventually find out why they're equal to these, right? But let's just do a question so you can understand how these are used. It says that express this product as sums or differences. So now you need to apply the thing that we did before. So it says 2 sine theta cos theta, and we already know that 2 sine alpha cos beta is equal to sine alpha plus beta plus sine alpha minus beta, right? And these are just subtle differences, but you need to know how to get them. Okay, so since 2 sine alpha cos beta, we can replace alpha over here with 3 theta and this beta over here with theta, and so you get this, and then just add them up. So this 2 sine 3 theta cos theta is equal to sine of, instead of alpha you have 3 theta, and instead of beta you have theta, instead of alpha again 3 theta, and instead of beta you have theta. So in the end you get sine 4 theta plus sine 2 theta, and that's really just as simple as that. Now let's see the products of sines and cosines and how we can express them as sums and differences. So it's basically the opposite of what we did before, but it's the same logic. You can get either one by the same process. So it says that if you have different combinations of sines and cosines, so for example sine p plus sine q, or sine p minus sine q, cos p plus cos q, or cos p minus cos q, you can see all of these are just differentiated by either the change in the trigonometric function, so it's either a sine or a cosine, and with the addition and subtraction signs between them, right? So how do these change the products? Well, there are very subtle differences like before. You'll have to deal with p plus q by 2 and p minus q by 2. Just remember that. And you'll have to see what function they are in. The functions are the only things that change in the product side of the equation, right? So for example, if you have sine p plus sine q and if you have sine p minus sine q, what's the difference eventually in the product side? Well, you can see that only the positive and negative signs are changing. So on the right hand side, the only thing that changes is the function. Instead of sine p plus q, you have cos p plus q, and instead of cos p minus q, you have sine p minus q. And so these are all the very, very subtle differences that exist in such questions. And yeah, you just need to basically just see the logic behind all of this, see all the subtle differences, and you'll easily be able to memorize all of these. But we're not concerned with that. We're more concerned with the question that is over here, right? So yeah, again, if you need to relate this back to the sums and differences of sine and cosine and how they're converted into the products, you just remember that p over here is a alpha plus beta and q is alpha minus beta, and you'll easily be able to understand why we get this, right? But again, all of these are related by the fundamental theorem, right? So yeah, here's the question. It says that sine 5 theta plus sine 3 theta, we need to express this sum as products. Okay, so we have already been given this right? Sine alpha plus sine beta is equal to 2 sine alpha plus beta by 2 into cos alpha minus beta by 2, right? This was in the previous slide. And so you can replace this alpha over here with 5 theta and this beta over here with 3 theta. And you'll replace them over here as well. And so you get this. Now just add 5 theta plus 3 theta over here and 5 theta minus 3 theta over here. And you get this. Okay. Obviously, because this entire term, if you write it down, it becomes, sorry, not this. It becomes sine 8 theta by 2. And so you can cancel this out and it's just eventually equal to sine 4 theta, right? And similarly over here, this becomes cos theta. And so you have 2 sine 4 theta cos theta. And this is how you converted this sum of trigonometric functions into a product term. Let's prove triple angle identities. So here's the triple angle identity of the cotangent 2x, right? Basically, it's just the reciprocal of the tangent 2x triple angle identity. And we need to prove how we go from this to this. So obviously, we'll take the left-hand side because going from a larger expression to a smaller expression is easier. And so let's see. Well, you can apply the difference of trigonometric functions formula on the numerator and the denominator, both, right? So once you do that, you get this. And if you remember, just to clarify how we got here, you remember that sine alpha minus sine beta is equal to 2 cos alpha plus beta by 2 into sine alpha minus beta by 2, right? And similarly, for the denominator, cos x minus cos 3x, you apply the same logic, right? And you get this. And now, further, you can just cancel out this 2 and this 2 and simplify whatever is inside the functions, right? So just to clarify, 3x plus x by 2, this becomes 4x by 2, which is just equal to 2x. And this here, 3x minus x by 2, this becomes 2x divided by 2, which is x. And this x plus 3x by 2, this becomes 4x by 2, which again is equal to 2x. So this is also equal to 2x. And this x minus 3x by 2 is equal to minus 2x by 2, which is equal to minus x, which is why you have this minus x. So now that you have this entire expression, what do you do? Well, now you can just basically take this negative sign outside with this sine function, right? Because sine is a odd function. So if you remember that sine of minus x is equal to minus sine x. So once you take this negative sign outside, it is multiplied with this negative sign, and eventually you have a positive denominator as a whole. Now, once you've simplified it this far, you can cancel out this sine x and this sine x to get cos 2x by sine x, cos 2x by sine 2x, which is equal to cotangent 2x, right? Because sine 2x by cos x is equal to tan x. So cos 2x by sine x, cos 2x by sine 2x is equal to cotangent 2x. And so you've proven the triple angle identity for cotangent. And again, the same logic can be applied for the tangent function as well.